Okay, good morning, Year 10, 11. We are continuing with differentiation, and where we're up to today, still working in Cambridge, is 8D, tangents and normals, and this new kind of notation which has a D, a Y, over top of a D and an X, and that's what we're going to have a look at today. This will follow on straight from 8C, and the way I'm going to explain this dy dx notation is basically using first principles. And I'll show you a little bit where that comes from. You probably don't really need to necessarily understand in great detail where this notation comes from, but we are going to be using it for the rest of the course, including in our Extension 1 course. So we're looking at the similar graph here to what we looked at in 8A and 8B, first principles. We're looking at small changes in X and Y. And this diagram is used to understand what this dy dx is. And we actually, the way we say it is sort of like dy and dx. That's how I will be talking when I'm saying dy dx. It's the letter D, not d, y, or dx, but dy dx. This dy dx notation is exactly the same as f of x. It's what we get when we differentiate. And we're going to be using that, as I said, all the way through. So have a look at our graph down here. We have the black line here, which is our function. We have 2 points sitting on that function. We have point P and point X. We have a secant or a line that joins PQ, and we have this green line, which is our tangent at P. So what we are doing is exactly the same, again, method as we used in our first principles. But what we had in our first principles was we had our point P being called X and f of X. Our point P is now defined as the point X, Y. So we'll pop that up there. P is our point X, Y. And so we're using Y instead of f of X, which we are very familiar with in the functions topic. Okay, Y was equal to f of X. F of X is equal to Y here, so it's exactly the same. What we did to find our point Q, or how our point Q was named in first principles, it was point X and we'd moved up a little bit, which was called H. What we're going to do now is we are going to refer to the movement from X up to point Q on the X coordinates as dx. Or this little d here, this is a funny looking little d. It's different to the letter D up the top here. It stands for delta, which is a small amount. And you might often see that delta, it's like a curly D written as a little triangle as well. It means change or delta. And the same is going to happen with Y. We're going to move up from Y, a small amount, to a delta Y. So our point Q is X plus a little bit more of X, delta X, and our Y coordinate will be Y plus a little bit more of Y, called delta Y. So we're going to call that X plus delta X is our X coordinate, and Y plus delta Y is our Y coordinate. Now, previously we'd worked out with our first principles what our gradient of PQ was. So gradient of our secant PQ, we used our rise over run, and we use that notation of y2 minus y1 x2 minus x1, which is just our rise over our run again. And that's the gradient of the red line. We want to do that again. If I do that, and you might want to pause this and have a little go yourself, the change in the y values is going to be y plus delta y, take away y. We're going to be just left with delta y on the top line, just over here. Our bottom line will be x2 minus x1. That'll be x plus delta x minus x. The x's are going to cancel out. We're going to be left with just delta x. So the gradient of PQ is delta y over delta x. Okay, so similarly, like our first principles, we looked at what happened when our h became really close to 0. We're going to have a look here what happens when our delta x is tiny. If our delta x is tiny, the part that we've added to x is going to be small. So what that will do will bring our point Q really, really, really close to P. Okay, so we don't want delta x to be 0. It can't be 0, but it's moving towards 0. So I'll just read this paragraph here. It says, when delta x is small, the secant PQ is almost the same as tangent P. So that was the same as our first principles. And the derivative is the limit of delta y over delta x as Q gets as close as we like to P, as in delta X goes to 0. This is the basis for the, and I can never pronounce this, Leibniz's notation. That is basically our dy dx. Now, you don't need to fully understand what's happening here so much. We can get through with just understanding what dy dx means in terms of the gradient of the tangent at the point. But this is where it comes from, and I know a lot of you would like to understand that. But that's where our little delta x and our delta y's come from. Okay, so let's have a look here. If delta y is a small change in y resulting from a small change in x, then we can write dy dx as the limit of delta x going to 0 of delta y, delta x. So this dy dx is what we've worked out up here, okay? It's the gradient of this green tangent at P. Our dy dx, okay, so we're going to write it as dy dx because we're not going to write the limit part each time. But this dy dx is not a fraction, okay? So be very careful about that. It's a change in our y over a change in our x. Now, we previously have been writing in the last couple of lessons f dash of x as our first derivative. We can still do that, but we are going to attempt to, from now on, write it as dy dx. They're the same thing, okay? Remembering that y was our function of x, okay? Dy dx is our f dash of x. They're the same thing. It's just a more superior notation, and that's the way we're going to try and write it. Okay, going down a little bit further here, it talks about second and higher derivatives. Now, I know a few of you have picked me up in class talking about this f dash of x here as the first derivative. And I've said, well, we are going to look at second derivatives and so on. So this is where we're just going to talk about it. We're not going to look at what it means, but just to let you know that it can happen. So the derivative of a function is another function. So it can in turn be differentiated to give a second derivative of the original function. So we can have a function, we can find that derivative f dash of x or dy dx, but we can also then find the derivative of that f dash of x. And if we do that, we're going to pop it a second dash in there. It's going to be called f double dash of x. Or if we were to write it in our Leibniz notation, we're going to write it as d squared y on dx squared. Now, just want to show you this and let you be aware of this. So for this function here, x to the power of 5 plus 5x to the power of 3, there are two ways we can write this function. We can write it as y equals, like that, or we can write it as f of x equals that. Okay, and we should be familiar with that because we've been doing that all the way through. I can differentiate this function and write it as dy dx, which equals, remember the 5 comes down the front, and we take 1 off the power, so we get 5x to the 4. The 3 comes down and times by the 15. The 3 comes down and times by the 5 to give us 15. We take 1 off the power to give us 2. Similarly, I could write that dy dx as f dash of x, and I do exactly the same thing because these are identical. Okay, dy dx, f dash of x. We could then go again. We've differentiated our function to get our gradient of the tangent, but that's still a function. So we could go again and write it as d squared y on dx squared. 4 times 5 is 20. Take 1 off the power, we get 3. 2 times 15 is 30. Take 1 off the power, we get x. We could also write it as f, and that's got a triple dash in there. That should be a double dash, not a triple dash. F double dash of x equals 20x cubed plus 30x. So they're the same. And we can continue that process on and on until we no longer have the function, a function that it will work for. So we could go to d cubed y on dx cubed, d to the 4th y, d to the power of 5 of y, and so on. We generally will be only dealing with these guys here, okay? But it's good to know that that's there for us to have a look at as well. Okay, scrolling down to have a look at example 11 down there, we're going to have a go at doing exactly what we've been talking about. Now, it's asking us to differentiate y is equal to 4 minus x squared. Now, we were writing it as f dash x. I'm going to write it as dy dx. dy dx is equal to, if I differentiate the 4, I'm not going to get anything. If I differentiate the minus x squared, note there is a minus, the 2 comes down, I end up with minus 2x. 1 comes off the power, it's x to the power of 1, and it stays like that. That's our first answer. Part B. Find the gradient of the tangent at the point P is equal to minus 1, 3. So the gradient of the tangent is what this is. Okay, when we're differentiating, we have found the gradient of the tangent at some point. Here we're being asked to find the gradient of the tangent at the point minus 1, 3. So I'm going to pick out the x as minus 1, and I'm going to pop that in to where my minus 2x is. I'm going to write minus 2 times my minus 1, which is equal to 2. So the gradient of the tangent at the point minus 1, 3 is 2. Okay, we're nearly there. Part C, find the point on the curve where the gradient of the tangent is equal to 6. Okay, so the gradient of our tangent, remember, is dy dx. And we've worked out that dy dx is minus 2x. And we're saying here that the gradient of the tangent, which is our dy dx, is equal to 6. So I've got minus 2x is equal to 6. I'm going to divide by minus 2. I'm going to divide by minus 2. These guys cancel out. I get x is equal to minus 3. Okay, now let's just double check the question. The question says find the point. We haven't found the point. We've only found the x coordinate, so we need the y coordinate as well. So we've got the x here. We want to find y. We're not going to substitute it back in here. We're going to substitute it back into our original function. Our original function was y equals 4 minus x squared. So y is going to be equal to 4 minus x squared. Okay, that is equal to 4 minus 3 squared is 9. 4 minus 9 is minus 5. So our point is the point minus 3 minus 5. And that is the point where, on the curve, where the gradient of the tangent is equal to 6.